Continuing your study of the area of a region enclosed by two curves, we're going to look at a different kind of situation from what we've seen in the previous video. Something a little bit more complicated, something like that, where we're looking for the area enclosed by two vertical lines as before, x equal a and x equal b, and also by the graph of two functions, just like before, y equal f of x, y equal g of x. The difference is that this time we no longer assume that one of the functions stays above the other over that interval from a to b. This time the two functions may intersect several times over that interval. So the area enclosed in that case is the sum of these three areas. And to do the calculation, we would have to calculate these three areas separately and add the results. So in this case, the first area here, we would have to find this point of intersection C between the two curves, and then you see that for this red area between A and C, the function f is above the function g, so the red area is the integral from A to C of f minus g, right? The function on top minus the function below, as we have seen in the previous video. Then for the next area, you see that the function g is above the function f, so we would have to find this second intersection point D, at our first coordinate D, and then this blue area would be the integral from C to D of g minus f, because this time g is above f. And finally, the last piece of the area enclosed by the two curves is the integral from d to b of f minus g, because f is again above g on the interval db. So that's a little bit of a pain to go through this, and practically speaking this is really what we have to do: find the intersection point, see on which interval which of the two curves is above the other, and calculate things this way. However, it is more compact and sometimes more practical to talk about this area, observing that this is really just the integral from a to b of the absolute value of f minus g. Because if I take the absolute value of f minus g, I always have the difference of the two functions with the greatest minus smallest. Because of course, I take the positive difference, and therefore on the first interval this absolute value of f minus g is f minus g because f is greater than g. On the second one, absolute value of f minus g is g minus f because g is greater than f, and of course on the last one it is f minus g again. Now in practice we don't really use this absolute value. We have to go down to finding the intersection point. So for instance, if we look at this exercise where we want to find the area of the plane region enclosed by the two curves y equals sine x and y equals sine 2x over the interval for x ranging from 0 to pi over 2. So we have these two vertical lines, x equals 0, x equals pi over 2. As usual, the first thing we're going to do is sketch the graph. Well, first, according to what we just have seen, we know that the area could be expressed as the integral from 0 to pi over 2 of the absolute value of the difference of the two functions. But to calculate that practically, we sketch the graph, and you see that the curve that takes its maximal value 1 at pi over 2 is sine x, right? Sine of pi over 2 is 1, whereas the curve that takes its maximum value at pi over 4 is sine of 2x, because if you plug pi over 4 in sine 2x, you get sine pi over 2, which is 1. And of course this function sine 2x takes the value 0 at pi over 2, because this is sine of pi. So the area that we're looking for, x ranges from 0 to pi over 2, and we're looking at the area between the two curves. So this one is sine 2x, and the area between the two curves is the sum of these two areas. To calculate them practically, we need to find the first coordinate of the point of intersection here. So to do that, we have to see for what x we have sine x equals sine 2x. So we set this up, and here it's not transparent how to solve this kind of equation, but you may remember the double angle formula. For the sine, it says that sine of twice an angle is 2 times the product of sine and cosine of the angle. In other words, this is 2 sine x cosine x. If we remember that, then the equation becomes a lot easier to solve, because now we can put everything on one side and factor out sine x. So we get sine x multiplied by 1 minus 2 cosine x is 0. And if a product is 0, it means one of the factors is 0. So either sine x is 0 or 1 minus 2 cosine x is 0. In other words, either sine x is 0 or cosine x is 1/2. Because x here is restricted to the interval 0 pi over 2, sine takes a value 0 only at 0, and cosine x takes a value 1/2 on the interval 0 pi over 2 only at x equal pi over 3. So the x coordinate of this yellow point of intersection is pi over 3. So that will give us a way to set up our integral. Namely, so now to obtain the area, instead of using the absolute value of the difference, we're going to be able to write explicitly what it is. So from 0 to pi over 3, the function sine 2x is greater than the function sine x. So if we set up the integral from 0 to pi over 3 of sine 2x minus sine x, that will give us the red part of the area we're looking for. And then we're going to add the blue part, which is going to be the integral from pi over 3 to pi over 2 of sine x minus sine 2x, because on that interval sine 2x is greater than sine x is greater than sine 2x. So this is what we obtain, and now all we need to do is find antiderivatives and evaluate at the proper values. An antiderivative of sine 2x is negative 1/2 cosine 2x. Antiderivative of sine x is negative cosine x. So what we obtain looks like that. We have negative 1/2 cosine x, negative 1/2 cosine 2x plus cosine x that we evaluate between 0 and pi over 3. And then the opposite function, which is the antiderivative of the opposite sine x minus sine 2x. So that's going to be negative cosine x plus 1/2 cosine of 2x that we evaluate between pi over 3 and pi over 2. Plugging things in, we obtain something like that. So when we plug pi over 3 in the first function, I get this negative 1/2 cosine 2 pi over 3 plus cosine pi over 3. When we plug 0, since cosine 0 is 1, we obtain negative 1/2 plus 1. Of course, we're going to take the difference. And then for the second function, when we plug in pi over 2, I get 0 for the cosine, and I get 1/2 cosine of pi, that's negative 1. So I get negative 1/2. Then I subtract the value at pi over 3, which is negative cosine pi over 3 plus 1/2 cosine 2 pi over 3. So you see that we have, for the things that do not contain the cosines, we have 1/2 minus 1 minus 1/2. So that's just negative 1. And then for the other terms, we have 2 times cosine pi over 3, and cosine pi over 3 is 1/2, so that's 2 times 1/2. And then we have minus 1/2 of cosine 2 pi over 3. So that's just minus cosine of 2 pi over 3, and cosine 2 pi over 3 is negative 1/2. So we get this negative 1 plus 1, that cancels out, minus negative 1/2, so we end up with positive 1/2.